the main thing that we're going to be studying in Chapter 4 is polynomial algebra, mainly adding, subtracting, multiplying, and dividing. And in Chapter 5, we're going to talk about factoring, one of the most important ideas in intermediate and college level algebra. But before we do that, I want to review the rules for exponents and also shift into scientific notation because it's very much the same, using the same properties, that is. All of these rules I expect you guys to know already, but the main focus, like usual in the college class, is to think about, well, why are these things true? Because I don't know if you were like I was when I was in high school or a student or whatever. I was always good at math. That not everybody is that way, which is totally fine. But for me, I didn't always necessarily care about why I was doing things or the reasoning. I just kind of was good at learning the rules and repeating them. And not that was a bad thing, because I was always very able to do it, but I didn't necessarily have a sense behind what I was doing. And that sense is really critical to mathematics as a whole. And if we don't know why, what's the point of doing anything to begin with? But basically, the exponent laws that we're going to be focusing on, you can see on the screen there. But there are rules such as, well, if I multiply exponential expressions with a common base, what we do is we add the exponents together. When we divide, we subtract, so on and so forth. So I really wanted to establish the reasoning behind all of these rules and why they're true. And what's nice about most exponent rules is that the reason that they're true is just based on what the exponent notation means to begin with. So let me shift back to my whiteboard. That way I can do some examples and start talking about some of these rules. And the packet for today's class is just a smattering of various practice questions, which we'll work on some of these soon. But what I want to focus on first are, what are the rules and why are they true? So let me make sure my tablet's ready to go. But let's start with the very first one, which is that if I have a to the m multiplied by a to the n, where a is anything, and the main thing that's important about that is the consistency of what is the base. Excuse me. So the base is just the term in an exponential expression. The base is always just the number on the bottom, and the exponent is the number to which we're raising that base to. So like let me throw some numbers in there. So say for example I had 5 to the third power, and I was multiplying this by 5 squared. By that rule, what we should do is we should add the exponents together and keep the base the same. A common mistake here is to actually also multiply the bases together, but when you're actually applying that rule, you only add together the exponents and you leave the base alone. It can kind of seem strange if you don't really get why it is what we're doing. And looking at the practice questions on the packet, well, let's say we want to do 3 to the 6th times 3 to the 11th power. That would make 3 to the 17th power by the same rule. But again, well, why? So if I think about what the notation actually means, well, 5 to the third means 5 times 5 times 5. So I could literally write that as an expanded multiplication of things, because that's always the inherent meaning of what 5 to the third means. And well, what I'm trying to do is multiply that by 5 squared, which means, again, well, 5 times 5. And if I think about, well, what's 5 times 5 times 5 times 5 times 5, of course, that makes a string of 5 5s, Yahtzee, and that, of course, we could write as 5 to the 5th power. So the reason why when I exponentiate the same thing, 2 different powers, or even if they're the same, it's an additive effect, because really I have a chain of multiplication. This is just a bunch of multiplication, as is this. And if I multiply a bunch of multiplication together, what I get is a bunch more multiplication, a sum of all of those factors. Now, if the bases are not the same, like say 1 is 5 and 1 is 4, of course this rule doesn't apply. Only when the base is the same does the rule work, and the base never changes. The base does not multiply also when I'm using it. So the next rule is that if I have a division of 2 different exponents, it creates a subtractive effect, which is in essence the same exact, it's based on the same exact reasoning. Like say for example I had x to the 7th divided by x to the 4th. You know, if you apply the rule, what I would get is the base would stay the same, which is x, and 7 minus 4 would leave me with 3. That would leave me with x to the third power. Cool. But again, why? Let's just use an example with numbers. Let's say we're doing 5 to the third over 5 squared. Well, if I were to write them out in expanded form as I did before, what I would have is 5 times 5 times 5 over 5 times 5. Or if you were to just do the math, right, that's 125 divided by 25. And if I took 125 divided by 25, that would actually just leave me with 5 due to the property of fractions, which is the common factor property. Or there's various ways that this property is phrased. Sometimes it's called the equivalent fraction property, but anytime a fraction, if it's written in a factored form, if there is a common factor on top and bottom, I'm allowed to cancel out the common factors. And again, this rule only works when they're multiplied, not any other circumstance. Much like this rule up here, one thing you never want to do is say I had 5 cubed plus 5 squared. That would not make 5 to the 5th power. Definitely not. Only when it's multiplied does that make any sort of sense. And there is no synonymous rule for adding exponential expressions. Same with subtracting. It doesn't work in the same way. But in this case, what I'd be left with is 5. And if factors fully cancel out, it always leaves me with 1. If you wondered, well, why does it leave me with 1 and not 0 here? It's just because technically, when I'm multiplying things, if you multiply by 0, it always makes 0, which is never equal to what's left over. So when you're canceling things in some contexts in math, you're left with a 1 instead of a 0 because in this case we're multiplying, and when we cancel them out, it's kind of like we're dividing by a common factor. And when you divide 5 by 5, you're left with 0, you're left with 1. But anyways, we're left with 5 over 1, or 5. But notice what that leaves me with is, well, if I were to use the subtraction property, 5 to the third divided by 5 squared should just be 5 to the 3 minus 2, which is of course 5 to the first. And anything to the first power is always equal to itself, because there's only one of those things. And basically, you know, that's kind of the reasoning why it works, is when I'm dividing by exponential expressions, they subtract. And notice it's pretty much the same rule. When you're multiplying, it creates an additive effect behind the exponent. When you're dividing, it creates a subtractive effect for a very, very similar reason.